So, hello students. The last lecture was actually based on just many of the questions of the text given in the NCERT exercise. Now we will discuss about some more questions and their concept from the exercise. Okay. One by one, some important question I will choose from the exercise and we'll try to get the answer. Okay. Based on the different theories given in this chapter and different concepts given. So let's start from the question number first only, 9.1. Explain the bonding in coordination compounds in the terms of Werner's postulates. Bonding. There are actually primary and secondary kind of bonding, means coordinate bonding and the ionic bonding. Already I explained that according to Werner's theory, there are two different kinds of bonding available in the coordinate complexes. The one type of bonding that is actually ionic bonding, which is actually stand for the counter ion and the complex ions. And the second type of bonding based on the coordinate bond with the ligand bond with the central metal atom. The next question is about FeSO4 solution mixed with ammonium sulfate solution in 1:1 ratio. Molar ratio gives the test of Fe+2 ion. But copper sulfate solution mixed with aqueous ammonia in 1:4 ratio, molar ratio, does not give the test of copper or cupric ion. Explain why. Students, you should learn that the FeSO4 solution when mixed with ammonium sulfate, it will not form the coordinate complex formation. That's why the ferrous ion remain in the solution and sorry. Okay, so this will actually depends upon always the qualitative test of any ion or radical depends upon the availability of that ions or radicals in the aqueous solution, because whatever the materials reagents we are using through the different aqueous solution, that will just give the presence of the given radical, the free radicals in the given solution. On adding of ferrous sulfate in the ammonium sulfate ion, that will just free the ferrous in the solution, because there will be a Mohr salt, Mohr salt formation. Mohr salt formation, you are knowing the formula, ferrous sulfate, ammonium sulfate as the formula. So these are the conditions why ferrous ion can be detected from the solution. But on addition of copper sulfate with the aqueous ammonia, that will give you a coordinate bond. And you are knowing, after formation of coordinate complex, now the metal ion is no longer free. No longer free. So the metal cation cannot be detected from the solution. The other question based on the ligand nature, IUPAC naming. So I will just go for the question number 9.5. 9.5, specify the oxidation state or number of the metals in the following coordination entities. Oxidation number, the calculation of oxidation number is just the same method given in the class 11th level, the redox chapter. The same method can be you can use to identify the oxidation number or oxidation state for any given complex. For example, suppose we have a formula CO H2O Cl En 2 plus. Suppose we have this compound and we will try to calculate the oxidation number of cobalt. So you can know, you should know, this water molecule is a neutral ligand. There will no any oxidation number. Cyanide will carry a -1 charge, and this will again a neutral molecule. So cobalt, the oxidation number of cobalt will be X plus plus 0, 2 equal to 2 plus. This will be giving you 0 and 0, so X will be plus 3. The cobalt carry positive 3, means plus 3 oxidation number. Water and ethene 1,2-diamine, these both the ligands are neutral ligands. So oxidation number always depend upon the charge of the complex or the charge of the ligand. And with the help of the charge of ligand and the charge of the complex, you can identify the oxidation number of any metal cation. The same time, you can practice for the IUPAC naming of the same complex as well. Suppose we will try to deduce the IUPAC naming of this compound. Can you guess what will be the oxidation of the IUPAC name? There are 3 different types of ligands. The name of ligand is aqua. This one is called cyano, sometimes cyanido, and this is called ethane 1,2-diamine. The IUPAC name of ene is ethane 1,2-diamine. You are knowing here is a numeral prefix we have to be used, that is called BIS, bis. Then we have to be arranged all these 3 ligands according to the alphabets. Aqua, and here is ethane, here is cyano. So the name will start from aqua. Then bis, ethane 1,2-diamine, cyano, cobalt, oxidation number 3rd in Roman. So this will be the name of this complex. I will write the name. Aqua, bis, this is the name of this compound. This complex name is aqua bis ethane 1,2-diamine cyano cobalt 3rd ion. If the complex carry charge, it should be mentioned here ion. If the complex having some counter ion, so there should be mentioned the name of the counter ion. Name of the counter ion. It will be the same way. So this is the possibility. This next question is about using IUPAC norms. Write the formula for the following. There are some IUPAC names are given in the exercise, and you have to be just write the formula of the given the inorganic complexes. For example, the first complex name is hydroxido zincate second. Tetrahydroxido zincate second. Zincate means the complex is anionic. So the formula will be, you first mention the bracket, there will be zinc hydroxido, tetrahydroxido, ZnOH4, and this complex should be carry -2, because after putting here -2, Zn can carry a +2 oxidation state. So oxidation state is given here, zincate second. So on the basis of IUPAC norms, you should be write first the metal name, then ligand name with the number of ligands and the charge present on the complex. The same way, you can use any of them to write the formula. Suppose diamine, dichlorido, platinum second is the complex name. Diamine means NH3 twice. Dichlorido means Cl2. Platinum second. So the formula will be PtCl2 NH3 twice, and the whole bracket must be carry. The whole bracket must be carry. What should be the charge? What should be the charge? Anyone? Dichlorido platinum. Look at the possibility. PgCl2NH3 PgCl2NH3 twice, and the oxidation number of platinum is second. Oxidation number of platinum is second. So what should be the charge present here? What should be the charge present here? The charge should be, hello, the charge should be, any guesses? Okay, the charge should be 0. Charge should be 0. Actually, students, this complex should be neutral, because when the complex will carry 0 charge, this 2Cl2 minus will give the platinum second oxidation number. Same way, you can just write the IUPAC name of the given compounds in the 9.7 question number. Now we can move for the valency bond theory questions, because that are the important one given here. And we can start from the question number 9.13. Question number 9.13. The question is aqueous copper sulfate solution blue in solution color. Aqueous copper sulfate. Aqueous copper sulfate is blue. Actually, aqueous copper sulfate is blue because of coordinate complex formation of copper second with the water molecule. And look at the possibility. So copper sulfate aqueous is blue because of the formation of this kind of complex. Whenever the white amorphous powder of copper sulfate is mixed in water, it just take out the 4 water molecule from the solution to form a coordinate complex. This is due to the splitting of the deep orbitals of the copper, that will give you a blue color of the copper. This complex tetra aqua copper. Okay. Now the question is a green precipitate with aqueous potassium chloride. This solution, when added in a potassium chloride, it will produce a green precipitate. A green precipitate. So look at the possibility. The green precipitate of this complex is due to the formation of another complex formation of copper second ion with the chloride. And now the charge is +2. So this is the condition why the green precipitate, a green precipitate is formed. During addition of this molecule, the copper sulfate molecule in the potassium chloride, there will be a green precipitate. This is due to the formation of this complex. And the next one is a bright green solution with aqueous potassium chloride. With aqueous potassium chloride, there should be minus charge now. Copper carry +2 oxidation state. So there should be minus charge. There should be minus charge, -2, because that -2 will balance the chloride and chloride together separately to give a copper +2 charge. Okay. So question is 9.13. Why aqueous copper sulfate is a blue in color? Because of the formation of this complex formation. Now, why there is a green precipitate? Because of the formation of this complex formation. And why there is a bright green solution? Because of formation of this complex formation. And you are knowing the color of the complex always depend upon the splitting of the d orbital, the delta value, the energy value, and of course the nature of ligand. You can see the three ligands are there. Due to the different ligand, the splitting will be differently. The delta value will be different, and that's why the different wavelength of the light can be absorbed and emitted complementary will decide the different color. The next question is, what is the coordination entity formed when excess of aqueous cation is added to an aqueous solution of copper sulfate? Why is it that no precipitate of copper sulfide is obtained when H2S is passed through this solution? Okay, so let's discuss the question number 9.14. The first possibility is, what is the coordination entity formed when excess of aqueous cation is added to an aqueous solution of copper sulfate? Aqueous solution of copper sulfate means this. Excess of cation is added. So 4Cn minus will replace the water molecule, and there will be formation of this complex. So aqueous copper sulfate, when added with the excess of the potassium cyanide, the cyanide ion will replace 4 water molecule from the complex and will give you this complex. This is a tetracyanide-cuprate ion, second ion. Okay. Now the question is, why is it that no precipitate of copper sulfide is obtained when H2S is passed through this solution? When H2S is passed through this solution, no precipitate formed because H2S does not react with this complex. Why does not react? Because this complex, the tetracyanide-cuprate second ion, is very stable. So when H2S gas is passed through the solution, there is no reaction, no interaction between H2S gas and this complex. So because of no reaction, there will be no precipitation formation. Next one is 9.15. Discuss the nature of bonding in the following coordination entities on the basis of valency bond theory, and the complexes are 9.15. The complexes are FeCN6 minus 4. You are knowing, on the basis of valency bond theory, you should first give you the idea of inner complex and outer complex, magnetic behavior as well as paramagnetic or diamagnetic, and hybridization, sp3d2 or d2sp3. You can see this is a hexa 6 ligands are there, monodentate 6 ligands are there, 6 Cn minus, so the charge of Fe will be Fe plus 2. You should start from the beginning. As complex, you just see the complex and just write the oxidation number of the metal. Now the oxidation number of metal is plus 2, Fe plus 2, okay, got it. Fe plus 2. Then you should write the electronic configuration of Fe plus 2. That should be here 3d6 4s0. 3d6 4s0. Now we are knowing the cyanide is a strong field ligand. So there will be splitting of d orbitals. But the problem is, according to the valency bond theory, According to the balancing bond theory, this splitting and the electronic configuration of T2Z and EZ was not explained. So you should only write the complex will be inner or outer. For that, you should be learn here the cyanide having tendency to get pair the electrons in the d orbitals. That's why the configuration will be the hybridization will be D2sp3. The hybridization will be D2sp3. So this D2sp3 give you a inner complex formation, and because of pairing of electron, there is even number of electrons also present, so there will be a diamagnetic behavior. So this complex, the complex of iron with cyanide will give you a inner complex formation, diamagnetic nature, D2sp3 hybridization plus 2 oxidation state. And if you can explain, if you want, then I can explain on the basis of crystal field theory also. If you just add some of the portion of crystal field theory, you can write the electronic configuration in the different set. T2G6, EG0, splitting will be high because of strong field ligand. Then all these things can be explained on the basis of both the theories. The same way, FeF6 minus 3. FeF6 minus 3, you are knowing the F6 means fluoride. Fluoride is a weak field ligand, so there will be no pairing of electron. So electron will remain unpaired. That will give you a paramagnetic behavior of the complex. Outer complex formation takes place. These things can be explained. And F6, 6 ligands are there. Octahedral, sp3 due to hybridization. Next complex is oxalate. Oxalate is also a weak field ligand, but some of the case it can be paired the electron, some of the case it cannot be. But here in the case of cobalt, actually there will be a pairing of electron, so D2sp3 hybridization takes place. On COF6 minus 3, there will be sp3 D2 hybridization takes place. Next question is 9.16. Draw figure to show the splitting of the d orbitals in an octahedral crystal field. So splitting of the CFT for octahedral I already explained in the previous lecture, so you can go through the previous lecture to explain, to learn all these. What is spectrochemical series? Spectrochemical series is actually the series of the ligands based on the increasing order of crystal field stabilizing energy possibility. In the extreme right, there is strong field ligands are actually placed, and in the extreme left, there is a weak field ligands are placed. It will actually depend upon the value of delta that can be imposed by the different ligands. So the series based on that value also. Next question is, what is the crystal field splitting energy? How does the magnitude of delta O decide the actual configuration of the d orbitals in coordination entirety? So crystal field splitting energy is actually when in the presence of external electric field, which is actually created due to the presence of ligands, there is a splitting of the degenerate orbitals of the inner d orbitals. And the difference, the energy gap between two different sets of the inner d orbitals on splitting is called splitting energy. For octahedral, the higher energy set is called EG set and lower energy set is called T2G set. So you can just mention a line. The energy gap between EG orbitals and T2G orbitals is called crystal field splitting energy. For delta, for octahedral, it is just denoted as delta O. The next possibility is how delta O will decide the actual electronic configuration of d orbitals. So students, for strong field ligand, the delta value is greater than the pairing value. That's why the electron will remain paired. They get paired in the T2G set, which is a lower energy orbital. So for that, the electronic configuration can be changed. We can take an example to explain this theory. To this question, the D4 electronic configuration can be written as a two different possibility. The one possibility is T2G4 Eg0. The second possibility is T2G3 Eg1. This will depend upon the delta value, the crystal field splitting value, and pairing energy. If the crystal field splitting energy is greater than the pairing will occur in the lower energy orbital, and after pairing of all the electron in the orbital, the next electron will enter in the Eg set. But if there is a weak field ligand present, that will have a low value of delta, which is generally lower than the value of pairing energy. So the electron will remain unpaired and will enter in the higher energy orbital called Eg orbitals. Next question is the chromium. The one complex is given. Chromium NH36 to the power plus 3 charge on the complex is paramagnetic, while NiCN4 minus 2 is a diamagnetic. Explain why. So look at the possibility. Look at the possibility. Students, see first. This complex is given here paramagnetic, while this one is diamagnetic. The paramagnetic behavior depends upon two things actually. The nature of ligand, which can be paired electrons in the T2G set, due to which the inner orbital can be used during the hybridization and no unpaired electrons remain there. That will decide the diamagnetic, and the electrons are unpaired remain, that will decide the paramagnetic. Look at the possibility. The possibility is this is called lower T2G orbitals, this is called higher Eg orbitals. In the case of chromium, the oxidation number is plus 3 and the configuration will remain D3. The configuration will be D3. D3 means the 3 electrons present in the D orbital. So electron will first, according to the Hund's multiplicity rule, the electron will remain unpaired in the T2G, then the fourth electron will get paired. This is why the inner complex formation of this complex will also contain the 3 unpaired electrons. This complex will, inner complex formation will be there, but it still will contain a 3 electron as unpaired because of the Hund's multiplicity rule. The fourth electron will be paired here, then fifth and then sixth. So the configuration less than D6 will always give a paramagnetic behavior of complex. The complex will be diamagnetic for inner complex is only when there is a D6 electronic configuration present. In the case of NiCN4 minus 2, there is oxidation number of nickel is plus 2, that is called D8. That is called D8. In the condition of D8, all the electrons will get paired. All the electrons will get paired in the inner d orbital, and the last orbital of the inner d orbital will hybridized to give you a dsp2 configuration. So due to dsp2 hybridization, all 8 electrons will get paired in the inner d orbital and will give you a diamagnetic behavior of the complex. This will be the explanation of these two compounds in the question. Next question is about a solution of NiH2O6 plus 2 is green, but a solution of NiCN4 minus 2 is a colorless. This again depends upon the color of the possibility will depends upon the DG transition. The electrons should excited from the lower T2G orbitals to the higher Eg orbitals. and that dd transition of the electron will decide what wavelength of radiation can be absorbed and what complementary wavelength will be emitted. That will decide the color actually. In the case of Ni S2O6 complex, the water is a weak field ligand that will give unpaired electrons in the inner d orbital, and due to the presence of unpaired electron, these electrons can be excited on the presence of light and will absorb the wavelength, will absorb the wavelength of light in the visible region. So complementary color will be a green, I think, green. But in the case of NiCl4-2, there is no any electron present as unpaired. All electrons are paired. There is no any excitation takes place during the light passing through the solution. So the color of the complex will remain colorless. Okay, so these are the contributory topic from the chapter. Okay, you can go through the other of the question from the NCERT exercise, and if there is any problem you can ask me that anytime. Okay, I am concluding my lecture here only. Two lecture based on the exercise and in-text question. The previous lecture number 10, and this will be the lecture number 11, I think. Lecture number 10 and lecture number 11 will based on the only questions and answer discussion. So you can go through both the lectures that will be available on the website for the completion. From Monday onwards, we will decide the next chapter, that will be chemical kinetics. Okay, good day.